Interacting with a computer might have been a very different experience if the research of Dr. Douglas Engelbart was never funded. In the 1960s, the Air Force Office of Scientific Research, now a part of the Air Force Research Laboratory, awarded a basic research grant to Dr. Engelbart. His research was to focus on augmenting human intellect and the potential for computers to assist people in complex decision-making. In 1961, Dr. Engelbart sketched a device that used a pair of small wheels rolling on a flat surface. The two wheels corresponded with the computer display's X and Y axis. The computer could track their combined rotations and move the cursor on the display accordingly. The AFOSR grant allowed Engelbart and his research staff to compare off-the-shelf pointing devices. Engelbart also reviewed his earlier notes with his lead engineer, Bill English, who built a prototype of the sketched input device. This was the first computer mouse, so named because of its superficial resemblance of the cute rodent. The mouse decidedly won, and was then included as standard equipment in their research moving forward. Engelbart and his team would go on to make significant contributions to what would become the graphical user interface, and were involved in the development of ARPANET, the precursor to the Internet. The mouse has evolved from a simple wood block with metal wheels to a solid-state, laser-driven device with many different features and options. With over 1 billion units sold, it is the indispensable device for controlling modern computers. Humans need air to live. Our lungs work best at sea level. Airplanes are most efficient at high altitudes, where the air is thin and smooth. This dichotomy means we've invented a machine that thrives where we don't. From the beginning of high-altitude research, flyers coped with thin air by inhaling oxygen through rubber tubes and later form-fitting masks. In 1937, researchers for the Army Air Corps began research flights in a modified Lockheed Electra. This airplane, the XC-35, was the first airplane built with a pressurized cabin. The fuselage had a circular cross-section to eliminate stress points. Its windows were made smaller and openings were sealed. The inside cabin became a pressure capsule, much like a large soda can. Within 5 years, both the B-29 bomber and the 307 Stratoliner began flying in pressurized comfort above 20,000 feet. Turbofan engines compress incoming air with a series of blades right behind the fan. At highest pressure point, some of this hot air is diverted. This bleed air is sent to de-ice the wings, operate pneumatic systems, and some starts its way to the cabin. The hot pressurized air is cooled in an intercooler and is directed to the plane's belly, where an air cycle refrigerator cools it further. The pressurized air is now mixed with the air from the cabin in a manifold and is moved by fans into the cabin. To maintain pressure in the cabin, incoming air is held by opening and closing an outflow valve. This valve is regulated by pressure sensors. The pressurized cabin is like a balloon that has a leak but is being constantly filled. From the smallest business jet to the largest airliner, the Air Force Research Laboratory's research and development of pressurized cabins have made modern flight accessible, safe, and comfortable. The point of impact, where physics carry the moment and only the car's safety devices can prevent serious injury or death. Many lives have been saved in crashes due to technology developed in the Air Force Research Laboratory. The rocket sled of Holloman Air Force Base was the dangerous test environment of Colonel John Stapp. In the early 1950s, he was tasked to test human tolerance to deceleration in an effort to develop protective technologies from crash forces. His sled accelerated for nearly a quarter mile to attain aircraft speeds. Stapp then was subjected to aircraft crash deceleration energy. Metal scoops beneath the sled plowed into a trough of water for braking. In 1954, Colonel Stapp rode his sled, the Sonic Wind, at 632 miles per hour. Upon the sled's rapid braking, he came to a dead stop in 1.4 seconds. This exposed him to more than 40 times the pull of gravity, proving that wind blast and deceleration from ejection at high speeds could be survived. Time magazine called him the fastest man on Earth and #1 hero of the Air Force. While testing at Holloman Air Force Base, Colonel Stapp noted that the Air Force lost nearly as many men in fatal auto accidents as in plane crashes. So he began a car crash study program. He put test dummies into salvaged autos and projected them into wood and concrete barriers. He also used human volunteers in his rocket sled to test safety belts up to 28 Gs, or 4,800 pounds of force. In the mid-50s, an average of over 50,000 Americans were dying in auto accidents each year. Colonel Stapp's research changed that. Colonel Stapp convened the first independent conference dedicated to auto safety. The focus was not on preventing the crash, but on preventing death and catastrophic injury when the crash occurs. Doctors, engineers, and scientists from all over the country assembled at Holloman to witness crash demonstrations and to inspect Stapp's latest restraint system designs. He made the case for seatbelts and later for airbags as standard equipment in all American cars and trucks. Colonel Stapp achieved his major goal in the summer of 1966, when he and Ralph Nader stood in the White House Rose Garden alongside President Lyndon Johnson as the president signed into law the National Traffic and Motor Vehicle Safety Act. This led to the establishment of the Department of Transportation and the National Highway Traffic Safety Administration. Stapp was appointed NHTSA's chief medical scientist and immediately set about writing the inaugural set of federal auto safety mandates. 2 years later, seatbelts were standard equipment in American cars, and traffic fatalities began to fall. With airbags, seatbelts, and crushable bumpers, it is now possible to survive even a head-on collision at highway speed. Many today have walked away from crashes that would have been fatal without the safety features pioneered by Colonel Stapp and his team. The innocuous GPS blue dot. It's easy to take for granted, this little dot that is available to us with a simple tap on a mobile device, virtually anytime, any place. But have you ever wondered how that blue dot got where it is and how it works? The answer may be surprising. The space race began in 1957 with the Soviet launch of the first artificial satellite, Sputnik 1. This man-made moon orbited our Earth flying overhead in an elliptical flight path. Its only transmission was a constant beep. Two physicists at Johns Hopkins Applied Physics Laboratory quickly realized they could surmise the position of a satellite in orbit by analyzing the Doppler effect of its constant radio transmission. The Doppler effect is the change in frequency of wave for an observer moving relative to its source. It is most noticeable when the sound of an approaching vehicle goes up in pitch and then lowers as it drives away. Radio waves and light are also subject to Doppler shift. In 1958, Geyer and Weifenbach used this knowledge to do the inverse of their initial success. They were able to pinpoint a location on Earth if a satellite's position was known. In 1960, the United States Navy began using the first satellite navigation system, Transit, to provide navigational fixes for submarine-launched ballistic missiles. Its accuracy of 2 miles was sufficient for nuclear missiles, but lacked the precision needed for more conventional warfare. The Cold War spurred the development of newer navigation systems. Transit was too slow for the high-speed flight of the United States Air Force, who ultimately decided to develop its own system. The United States Army also launched into orbit its own surveillance satellite for use in location fixing. Each branch of the military was developing its own navigation system. However, the Pentagon deemed these multiple efforts redundant and inefficient. In response, the development of the Defense Navigation Satellite System commenced in 1973. After 5 years of joint service development, the first Navstar GPS satellite was launched from Vandenberg Air Force Base. 7 years later, the first full constellation of GPS satellites was in orbit. By 1994, the total had risen to 24. Each GPS satellite carries an incredibly accurate atomic clock, solar panels used for power and battery charging, transmitters on various frequencies, and various detection sensors. At least 4 GPS satellites are visible at any time on any location on the Earth's surface. Each satellite transmits its position and the current time at regular intervals. Imagine standing somewhere on Earth with 3 satellites in the sky above. If the distance to satellite A is known, then your location must be somewhere on the red circle. If the same is done for satellites B and C, your location is where these 3 circles intersect. GPS systems use spheres instead of circles to calculate location in 3 dimensions. Accuracy goes up as the number of satellites used in the calculation increases. GPS is used in the military to aid land, sea, and airborne navigation, cartography, surveillance, search and rescue operations, aerial refueling and rendezvous, weapons guidance, and a wide range of additional applications. The United States Air Force is the controlling entity for the U.S. Global Positioning System. Air Force Space Command declared the system fully operational in 1995, and in 1996, GPS was made available for civilian use. Early civilian uses for GPS include trucking fleets, commercial airlines, and law enforcement agencies. As GPS receivers shrink in size, its uses multiply. The first handheld units allowed hikers, hunters, and campers to navigate rough terrain, track animals, or mark favorite hiking destinations. GPS can be used for boating, fishing, and other water activities. Today, GPS receivers have shrunk down to one inexpensive computer chip. Besides the obvious use of navigation, onboard GPS receivers allow for geotagging of photos, checking in a location on social networks, tracking down stolen phones, and countless other uses. The blue dot, that simple location indicator, began with the launch of the first artificial satellite. Its creation was driven by the Cold War. Its development is the result of Army, Navy, and Air Force cooperation.